over to Aaron.
Hi, everyone. I'm Aaron Knoll. I work on OvS. Occasionally, I work on very experimental stuff. And so that's what this talk is going to be about, something very bleeding edge, maybe crazy, very experimental. It's called OvS and socket maps beyond ports as endpoints. I don't know if anyone knows, I've realized I forgot to put an introductory slide about socket maps. So I'll just very quickly say socket maps is an eBPF concept. It's for forwarding from one socket to another via eBPF program. So, it's like a bit faster forwarding. You use the PSOC infrastructure. I think it was introduced 6 years ago, 7 years ago, something like that. Yeah. So what we're going to discuss today, layers and how they maybe don't matter. Maybe they do. Bypasses, so like skipping stuff, but smartly skipping it maybe. Direct forwarding, some numbers, so like the performance people might get a kick out of it. And also, finally, a note, I didn't use AI for this talk, and I'm pretty bad at pictures, so sorry. Okay, so a question, Open vSwitch, is it a layer 2 switch, right? Packet comes in from, say, a network namespace or another computer over a physical. It does some ARP flooding via normal action, right? So that's layer 2. It's a layer 2 switch, right? I mean, sort of. I mean, yes, it is a layer 2 switch, but it's more than that. Layer 3 is there too, right? We can do controller and learn actions. We can do routing as part of rules. We can do all sorts of fancy things with matches and rewrites. We can pretend that like multiple subnets exist even when they don't. So it acts sort of like a router, moving packets around and isolating subnets, all that. And so yeah, we just illustration here, like going to Open vSwitch, then doing some flow rules match. I ran out of space for action, and then I realized it looks bad on this if I stretch it too far. So you just have matches. Sorry. Okay, but we also do. I think we're running out of battery. Anyway, we also do layer 4, actually all the way to layer 7, right? So we have full CT integration. We have helpers. We have all sorts of fancy stuff to track related connections and doing all sorts of tracking tables, windowing. It's like really feature-rich thing. It's more than just a switch. I mean, we call it vSwitch, but it's really like it's SDN, right? So it's all sorts of networking related stuff. Okay, and the layers are useful for diagramming, I think, and useful for kind of thinking about networks and how to move data around, and they're useful for constructing complicated networks. And you have like this giant sandwich of, I found this on the internet, but it's pre-AI, so I'm fairly certain it's not AI, so I did not lie to you. It's like this giant stack of layers that kind of maybe are very big, okay? So all right, what's actually happening? Let's think about it like that. So let's break down the layers for a minute, because maybe they're not useful. What's actually happening? An SKB with data, I mean, it comes because OvS module, when we install a vPort, we actually hook the receive path, and as part of KSoft IRQ, waking up for NAPI, it detects, okay, there's a buffer, it pulls the buffer, it runs it through the OvS DP execute path, and starts doing action processing. So notice I didn't say bridge. There's not really a bridge or anything. We're just walking across, like flow table. We're sort of building up a key that helps us with matches and all that, and then find some actions, and then eventually we figure out, okay, we have to output somewhere, and in this case, I'm only going to deal with the local node. So like someone sends from one network namespace from one pod to another pod on the same node, and it comes in through vEth and eventually hits that that BP execute path. Then we eventually find out it has to go through output, and then it hits an IP stack, another IP stack, where again it goes through a routing layer, and IP processing and TCP processing finally put on the socket object receive buffer. So like, I'm going to say it again. We have two processes. They're running on the same node. They're linked. We want them to communicate. We went through, I'm only showing one half of it, but we went through two IP stacks just because of layers. Okay, so for every packet, we go through all those layers. And the downside is, I mean, every packet will get, in OVS, every packet will get recirculated a bunch because we have all sorts of like complex CT and other matching that goes on. There's overhead for reparsing when we need to extract more fields and go deeper. There's the additional protocol work that happens as part of the individual network namespace stacks. And all of this whole talk, I'm talking again, all localhost. These programs are on the same system. They're in basically the same memory space. We know we want them to communicate, and we're making them do all this work. Yeah, it seems crazy, right? So what are we getting, right? Like, what are we getting for all that work? vSwitch already knows where is the packet going, right? It already knows it came from this thing. It evaluated everything, and then it knows, okay, it has to go into this network namespace. And us as the higher level sort of network coordinators, we also know there's some application running there, right? And we want these packets just to go to that application. Because vSwitch knows about IP, TCP information, it knows about CT information, it can know about other things like sockets and all that if it wants to. So what is the stack really providing us? I mean, like, we have all sorts of facilities already in OVS. We can do sampling, we can do counting and metering and all sorts of stuff. So what are these extra stacks giving us? So I will show you like the cost, right, sort of. This is from RFC that I sent out with the proposal that I'm going to go over with socket maps. So this is without anything, right? No special socket map, no special extra changes, just basic system. And you see from network namespace to network namespace over a 10-second period, we average like 73 gigabits per second. And it's, I mean, it's fast. Like, if 10 years ago you told me, oh yeah, on your little Intel Nuke, you're going to get 73 gigabits per second of transfer and all that, I'd say, okay, let's go home. We're done. But today, maybe, well, yeah, today that's, I guess, feels like just normal, just a part of life. So, and I should also note, this is all just kernel. This is using OVS dpctl.py, which is part of the kernel self-test suite. I did enhance it for the next slide. Oh, and before I go on to that, so I'm saying that we're doing 7.3 microseconds, 7,300 nanoseconds per packet. These are 65K packets, so it works out to like 120 some odd thousand packets in a second. That's how I calculate the total cost. And I'll get to how I got roughly one microsecond spent processing the protocol overhead in the next slide, or the slide after this. So we have some alternative approaches. Okay, I discussed 4, and then Adrian and I have been discussing a couple more. And I'm going to go over a few of them now. And you'll see how, number one, how I got those numbers and what the numbers can be. Okay, so this is a simple output action. Again, pre-programmed with OVS dpctl.py. And in this case, we implement a proposal where we have a socket list in the kernel module. And we have an early detection as part of a flow rule that, hey, there's a socket available. And we directly forward into the receive buffer for that socket. Okay, so the application can get it right away. And as you can see, with that, we process around 23,000 more packets per second. It only costs us 6.1 nanoseconds per packet. Again, this is like napkin math, rough estimate. We got 84.5 gigabits per second. So this is pretty significant, right? This is like good. And this is just the output action. Okay, so let's see what happens with contract action. Contract, just a single contract, doing that, only gets 63 gigabits per second, which is, yeah, sounds like okay. But with that socket forwarding, it's the same result as here. So we get 20 gigabits per second more. That's pretty big. It's a lot. So, I mean, I don't know what we're doing. 8.2 microseconds per packet for contract. It's a lot. I mean, I know contract does a lot and it provides us a lot of features, but yeah, that's 2 extra microseconds per packet. Okay, what do the flow rules look like in that case? You know, I built some simple flow rules. They just forward between two VETH ports. And then we have some, I'm only showing, again, one side of it. It's a little bit more complicated because there's, you know, I have to do both sides and all. And I wanted to fit everything on the screen that was relevant. So I implemented this as like a thing where we stamp some tuple metadata to the SK buffer. We try to forward it to a known socket in a known socket table. If we miss, we have a fallback recirculation ID. And then on the fallback recirculation ID, once we know this is where we want to send out to, we commit a socket, if we can find one, in that target network namespace, and then we forward on the packet. So this leaves the control path intact, right? So we'll only forward data in this case. The control path can stay intact and process all the control packets, ACKs and, you know, fins and resets and all that, and those will correctly tear down things. You know, I would expect most of the time the revalidator will purge this particular flow because it will be idle in the side that's sending the data, and then the side that's just, you know, sending just ACKs and control, that flow should stay active. Yeah. And this is sort of an illustration of kind of what would happen. So SKB data would come in, we would do a sock try, we would look in the socket table. If we find the socket, we forward it. If not, we go through that normal output, you know, routing, TCP processing, all that other stuff. Okay. So this is like an in-kernel approach, like almost all in-kernel approach. And it's very easy to think about and put a diagram about. And I just ranted about that for layers, by the way. So, but it's easier kind of to think about. There's not too much extra heavy lifting in user space. There are some revalidator changes that would be needed, stuff to manage that socket table, all that. And it preserves the flow-centric nature of OVS. It would be fairly easy to sort of think about for OVS developers. But the downside is we need to have the kernel manage a table. And that is, I mean, it sounds simple, but it's not actually that simple to manage this. It's like another cache. And we're holding on to system level resources, right? Like sockets are important resources for the kernel, and we have to take references to them and hold those references. So we want to be very careful about that kind of work that we do. Okay. And that leads me to the next downside, which is we do have to manage those references to the socket objects. We need to make sure we're acquiring them correctly, releasing them at the right time, you know, all that. It's yet another cache, and we have to, you know, kind of constantly get get the states of all the sockets in the table. It's maybe not that great from like a implementation point of view for like the kernel. But then there's like this idea of a user space-centric approach. And this one I've been trying to work on a little bit with Adrian. And actually, I think I have it included here because I was originally still working on it. But after talking with Adrian for the last 2 days, maybe we found that it's not workable in the current state. So we might have to drop it. But the idea is we actually have, instead of having to manage a table, what we do is we have a SOC, a single SOC action itself, and that takes the network namespace and inode or tuple information and holds the reference that way. That's then bound to the action that's associated with that flow, so that as the revalidator detects that that flow becomes idle because no more data is sending, then it will tear that flow down. At that point, we release the reference. It's actually really easy to think about as far as a kernel implementation. The problem is the user space implementation is, I put hard there, but it's wrong. Actually, it's very hard, like extremely hard to do right. First, just getting the user space working is not that simple because we have to peer into a network namespace to which we don't belong. And there's not really any primitives to do that without transferring the entire process network namespace. So I tried doing some hacky thing with fork exec and sending some stuff back through a pipe, but it was like kind of causing stalls in the main thread, so I gave up on that. And we would need to be root for now for the RFC that I posted with this user space side. But actually, yeah, it's very hacky. We would have to introduce new primitives for it in the kernel anyway, my opinion. The other downside with this is you get very narrow. You get very narrow flows, meaning like there's no wildcards, there's no mega flows at this point. You would have a flow basically per socket, which is, I think it's okay, but maybe others don't think it's too nice. So, oh yeah, okay. I guess I didn't emphasize. I guess I edited these after drinking last night. So yeah, the user space modification side is very hard. It's a nightmare tracking those sockets. I mentioned this, right? Crossing that net NS boundary is really not allowed right now. Making sure sockets are in the right state requires rewriting the recirc stuff because, of course, on the first packet through, the socket that you're trying to deliver to may not exist, right? For instance, in the case of a SYN, no socket exists. It actually has to go to the IP stack. That has to allocate a socket, create it, put it in like the right state, and then by that point, we've already installed the flow. So then, like there's a nightmare going back through and rewriting it. Or then in the case of like CT actions that have come in, we would have to like somehow put the SOC call before the CT action, which involves like narrowing that flow completely and rewriting things that OVS isn't really designed to rewrite. So it's not great. We could add some kind of metadata for use by the classifier to help it narrow a little bit, but it's not. I don't prefer it. Okay, and then the final approach I'll talk about is this eBPF-based approach. And this is where we put a BPF program action. And in that case, I mean, sock map comes from eBPF, like the idea of it. And if we just call an eBPF program that can do this forwarding, I mean, that seems really convenient. We can have some eBPF programs and stuff listening on all the C groups and finding sockets as they come up and having a program that, actually does the forwarding and, the vSwitch can be coordinating, updating the map that we need. It's kind of sounds nice. So the upsides is it builds on eBPF and PSOC. Programming could be easier. Maybe we can preserve all that megaflow stuff. eBPF is constantly developed and getting cool stuff all the time. The problem is adding BPF actions. We've talked about it before a little bit. It's a big can of worms because you no longer have a lot of the debug and tracing and everything that OVS provides because you're now going into some user space programs that get installed. And yeah, maybe there's a way to do it, but it's yeah, we have to be careful about that, I think. And so that's why I put the downside also maybe it may be harder to debug. Okay, so now the real question is, I've presented those options. Maybe there's a few others like this this VNet. I forget the name of it, but it's like an eBPF V device. You know, I don't have too much of an opinion on what the best way to go is, right? I've posted some preliminary patches. I did get some feedback. Adrian sort of was more in favor of the sock try, the first approach that I was actually able to benchmark and show. Kong Wang also replied to my kernel patch. He said, just do BPF. This is like crazy. I don't know what it's not easy to know what the best way going forward is. There are some important trade-offs with each. And then one other crazy thing to think about is whether we should extend this. This whole idea is to make it part of the data path, so flow writers don't care about sockets. But a question I had also is, should flow programmers be application aware a little bit, like be able to write some kind of higher level destination output that says a specific, you know, application type by whatever that exists. I'm just, you know, I was just drinking and thought maybe it's an interesting idea, right? Okay, finally, some acknowledgements. I want to thank Mingxi for helping with some of my benchmarking with my original patch, also finding some pretty critical bugs in my original POCs that I was using. Adrian for giving lots of feedback. Mike Patrick helped with some internal code review. Eric Dumazet, Steve Heminger, Kong Wang, Elko, they all gave feedback on the kernel side RFCs. Eric didn't yell at me completely for doing it, so maybe it would be, maybe that sock try thing would be okay, I don't know. Yeah, so, all right. We have some time left, so questions.
Thanks for the presentation, super nice. Isn't it though oversimplification that you can just bypass the TCP/IP stack? In your case, it was on the receive side, so let's just think of that.
Yeah, I mean, what do you mean an oversimplification?
I mean, stuff may happen even on packets that contain for TCP packets. If they have data in them, they might still, I don't know, get dropped at some point in the stack for reasons. And with your direct output to the socket in the other network namespace, you just bypass all that.
Yeah, it's a good point. In this implementation, the way that sock try, like that sock forwarder worked, the socket had to have the proper matching tuples, and it had to be in the correct state to receive. So there are states that the socket goes in where it's not allowed to receive, and you know, then it wouldn't be established anymore, or you know, wouldn't have gotten to established. So
true, but you're bypassing the whole TCP/IP stack. So what if you have an IP rule that drops based on some, I don't know, random condition that happens to match only some of the data packets?
but yeah, that rule won't work.
So that brings me to your last slide. Maybe flow writers should be aware of this and only use it when it makes sense.
Yeah, well, I mean, one thing is I don't think this would be the kind of knob that's turned on like by default, for instance. I mean, there are major downsides to it besides just, you know, that case you're thinking. You're thinking as like a flow programmer, right? Like, okay, I want to make sure that that if I put in a rule, that rule is honored. But actually, there's a different issue, which is there are some facilities that like kernel stack provides. And we skip all those, right? So like, and those are maybe important things that users like. For instance, TCP dump wouldn't work because we're actually bypassing where that skbuf would be picked up for that. So
yeah. since we are talking crazy ideas, and in the space of, do we need to allow users, or do we want users to be aware of anything? The idea popped up in my head is, can we have something like a new type of output action, which is output IP port? And then you do a route lookup somewhere, maybe in the kernel, and you determine where the packet actually goes. You may find out the socket in the end, and then you can cache it. And you know when the routing table changes, you can subscribe to those events. So then you can change the destination. And it's maybe, I don't know, if we are talking users actually knowing where the packets are going, then it's probably easier to think about IPs and ports as a concept instead of like sockets and some low-level stuff like socket maps and stuff.
Sure, yeah. I mean, it probably, like, just in the case of CT, you saw how much time it takes to do those CT calls. And if there's a way to use something like that and correlate it with the contract and NAT information, like as that packet comes in and go through that output action, that in itself would save a lot. I know OVN, like some OVN workflows are using like 1 and 2 and maybe sometimes 3 calls to CT. So that's a lot of extra overhead for like moving this packet around. And yeah, even some additional output action that would let us bypass all of that work, or at least bypass it from a data path perspective might be good.
Maybe the question would be if there is actually an output action for IP import, if it would also work for not yet established sockets, so that you can even forward the SYN directly to the listening socket or something like that. So maybe then it gets even more crazy.
Yeah, that one's harder too, because at least if you go based on the established state, you know that the rules generally allowed some packet like this before. If you go directly to the listen socket, there may be, as Dimitri was saying, some kind of rule that would block even even an accept, and then that might be. But it's interesting.
I think you and Adrian already considered the option of optimizing more of the data path, and if the packet is being received, and instead of going through all the data path actions like source net, destination net, and all of that, right away that this is going to a socket. So you skip everything on the header, and you move the data directly to the socket. Is this something that you think it's doable at some point? I mean, considering what you are seeing at this point?
Well, yeah, I mean, that's what I'm showing here anyway, is moving directly to the socket. So I think it's doable, but the question is, there are edge cases that we need to be careful about, because as Dimitri was saying, someone could want some rule running or some rule engine that installs something that would eventually kind of break that connection, and it only in potentially one direction, which is the data direction. And now the problem is, like, the axe might be going back, which keeps the connection alive, and our stuff is forwarding along. So I think there's edge cases to consider for that forward directly to socket.
Like, just to build on what you asked, Flavio. We've been discussing this idea for the last 2 days, and one of the things that I was thinking today is trying to split out. It might be useful just to, approach all these ideas. Split out the two optimizations that we're talking about. So there's one optimization which is skipping the destination IP stack. Like once you end up with the final output, just skip the destination IP stack, which is in itself useful, but it also might be problematic depending on the situation. And then there is this other problem, which is skipping all the contract actions. Like if we could think of those as two independent problems, we might end up finding better solutions, or at least finding a solution for one of the problems and just leave the other one.
Okay, well, thanks everyone.